is Tang. Today I'm here with my colleagues Shomo and Natalie to talk about in-situ data analysis with Julia for E3SM at a large scale. The goal of this project is to detect extreme atmosphere weather events by analyzing large amount of simulation data from E3SM. E3SM is DOE's state-of-the-art Earth system simulation tool. It can generate a large amount of weather simulation data. Due to the very limited data storage capacity, the traditional post-hoc data analysis might only be able to analyze partial datasets generated from E3SM. To address that issue, we use the in-situ data analysis method in this project, so E3SM can directly pass the data to Julia for data analysis. In this talk, I will firstly talk about the coupling of E3SM and Julia. Then Shoma and Natalie will talk about the SSW and GV modeling. After that, I will show you the demo of running SSW. This figure shows the major component of our infrastructure to couple E3SM with the Julia runtime. E3SM is DOE's state-of-the-art Earth system simulation tool, and it's mostly implemented in Fortran and runs at a large scale by using MPI. For Julia, it currently supports only being embedded from the C language, so we wrote the C interface to enable calling In-Situ.jl, the Julia file from the Fortran-based E3SM. In that In-Situ.jl, we can plug in different Julia modules like SSW or SSW plus GEV data analysis modules. This slide shows the coupling of E3SM and the C interface. As you can see in the left box, E3SM calls three different functions in the C interface. JLinit does the Julia initialization job and only called at the very first timestamp. JLExit does the Julia cleanup job and only called at the very last timestamp. JL call subroutine is called at each timestamp of E3SM and does the data analysis job in the streaming way. If we look at the right box, that JL call subroutine in the C interface can load the in-situ.jl Julia file and also load the module in that Julia file. So when it's called, it wraps the data and passes the data to that Julia in-situ module for data analysis. So this C interface is also compiled with E3SM together with that Julia library. And here we show you the coupling of the C interface and the Julia modules. Julia features with just in-time compilation. So you can see in the left box, we fix the Julia file, module, and the function names in that C interface. Then we don't need to recompile the whole E3SM if we need to make changes in that Julia modules. The other thing is the MPI communicator. So you can see that in the right box, we use MPI.jl package to support MPI communication between different Julia MPI ranks. But the current Julia C bindings in the left box just support several basic data format. So we have to pass the MPI communicator in Fortran format in that C interface. So next, my colleague Shomo will discuss his SSW modeling.
Here we show an analysis pipeline that uses our in-situ Julia integration capability to perform climate data analysis. We are looking at an event called sudden stratospheric warming (SSW), which is defined as a major mid-winter warming that occurs when zonal mean zonal winds at 60° north and 10 hectopascal become easterly during winter and stays easterly for at least 10 consecutive days. In the top plot, we show SSW detected, and the highlighted days in red circle shows the days when the zonal mean zonal wind is reversed and the value is negative. And in the bottom plot, using a green rectangle, we show the data points that satisfy this SSW definition and would be needed to compute it. In our analysis pipeline, we have implemented this SSW measure in Julia and can run this code in situ. As shown, our Julia implementation first computes a partial SSW measure for all the processes and then uses a distributed communication to estimate the final global zonal mean zonal wind value. Our SSW-based analysis is expanded to a more sophisticated analysis pipeline as shown in this chart. Our goal is to study linkages between SSW and extreme surface temperature variations, and to do so, we use a generalized extreme value distribution modeling scheme. Based on whether SSW is detected or not, we keep track of two sets of GeV model parameters, one when SSW is not present and the other model that captures temperature variations after SSW is detected. The details of this GeV modeling scheme is discussed next.
I'm going to discuss one of the statistical models that we've implemented in our In-Situ framework. Specifically, we have demonstrated the modeling of daily maximum surface temperatures using a generalized extreme value, or GEV model. GEV models are useful for estimating the probability of observing rare extreme events, such as unusually high or low temperatures. On the upper left, I show two GEV models with different parameters to demonstrate how the parameters affect the probability of extreme events. Given a threshold x, shown by the dashed line, the black GEV model indicates less than 0.1 probability of extremes exceeding x, while the red GEV model has 0.25 probability. By estimating the parameters of a GEV model, we can estimate such probabilities. For example, after we fit a GEV model to the surface temperatures, we calculated as a summary of the model fit how likely is it that daily maximum temperatures exceed some threshold following an SSW event. The bottom right shows an example of this estimated probability across the United States based on one of our simulation runs, indicating a spatial pattern to the likelihood of extreme events. We based our code on the Turing package, which allows flexible statistical modeling, but we needed to implement streaming variational inference for the in-situ setting. Briefly, the streaming method replaces an original prior over the parameters with the variational posterior distribution from the previous time step, allowing us to quickly fit our models in a streaming fashion. We anticipate that the streaming variational inference framework will enable a variety of statistical models to be used in the in-situ setting.
This demo shows running E3SM with in-situ SSW data analysis on one of our local cluster. This run launches 118 MPI ranks on 2 nodes. We have a simple visualization setup here, like a listener and a plotter. You will see a real-time visualization in a few seconds. Here, just showing you about 30 seconds of running SSW because the whole run will take about 2 minutes. In the SSW code in the right box, the SSW code first estimate a partial sum of zonal wind values and locations, and then use a global reduction. So the real-time plot shows you the final SSW values computed by this Julia function. This screenshot shows the results estimated by the in-situ GV modeling that get triggered by SSW based on whether SSW is detected or not. As can be seen here, we are able to estimate the parameters of the GV models in situ while running our analysis pipeline with the E3SM simulation. And this is the summary.